this lecture there are some few slides that are introductory slides, very easy to be read, and just a short history of elasticity theory that was based on the work made by all the mathematicians and physicists, mainly French, as usual. Laplace, Poisson, but Hooke was British. Okay, small load. Why small? Because we are lazy. We don't want it to break. So we can imagine to knock the table. We don't want to stay here for 20 years on this table and to deform it permanently so that it's going to behave like a plastic solid, like mountains. If you wait for a few thousand of years, you can build mountains. But we're going to give a look to, how to say, relatively instantaneous deformations.
Video.
Pardon?
Video.
I did it. It's there. It's blinking. I don't. Small because we're going to move very gently from the equilibrium position. And now you see that now we have a sort of a problem here. Because, okay, we can imagine an initial configuration, we can imagine to apply force, that's Hooke's law. But we can imagine that now we can apply this force in different directions. That will give rise to the concept of stress. By the way, interatomic forces are going to react. We are going to create a restoring force, and if we release this perturbation, immediately the system will go back to the equilibrium, like the spring. You push, you will receive a pull. If you pull, you are going to receive a push. So, the good old Hooke's law. Nice. We studied the harmonic oscillators, starting from this force. We coupled them, we consider strings, we consider the atmosphere, sound waves, and stuff like that. How can we make a summary about this? Well, with this plot here. If we study force and deformation from the equilibrium, we get a line. Forever. But please remember that there are many ways to go out from the line. For example, if I take a very rigid system, after some perturbation, there will be a limit and the system is going to break. Fragile, brittle. Or maybe, beyond a given limit, it's going to deform in a permanent way. Plastic. So please remember, we're going to stay into the linear Hookean domain. We're going to generalize the concept of force, stress, reaction, deformation, we will call it strain, and we will put them together, generalizing Hooke's law. That will be the base of elasticity theory. And what we want to do is to apply the dynamics, and we want to find possible wave systems inside solids. The end of the story is that, yes, there are waves. They will be called at the beginning as P waves and S waves. You will understand why. One will be the generalization of sound waves in solids, but it will be more complicated because you can imagine that if you compress a solid, you will have also lateral deformation. And then you can imagine that a solid can be sheared, not a liquid, not a gas. And those will be S waves, longitudinal, transverse. Then we will see how these waves can propagate inside an infinite medium, but no fantasy. Then boundary conditions, reflections, refractions, interference, and we will see how these waves can generate also surface waves. And at a broader scale, these surface waves can interfere and generate, excite the free modes of the Earth. That's the end of the story. So we have to start with these basics here, and we have to generalize the concept of a force. Now, In one way, it's very simple to generalize it. We can imagine to have a sample of something that is limited by some areas, and we can imagine to apply a force, like a tension. And it's very easy to generalize the concept of force to that of pressure, the force per unit of area. Pascal, if you want, or bar, if you want to care about large pressures or atmospheres. Okay, so in one way, we have to use a different unit. Force is Newton, as we know, but over an area, it will become a pressure, a Pascal. Fine, but we will have also to define the possibility of having a force not only perpendicular to an area, but also tangential to an area. That will be the origin of the concept of stress. But in general, it's a force over a unit of area. You could say, well, it's a pressure. Please remember that pressure for ideal fluids, it's isotropic. You can measure pressure in whatever direction. If you have a barometer, okay, you don't have to be careful about the direction. The pressure that you're going to feel about the gas, it will not, in general, be dependent upon the direction that you're taking. For solids, it's different. But you can imagine how to have this sample and to apply a force per unit of area. That will be what we're going to call normal stress. Why normal? Because it's perpendicular to the area. But the news is that if you take a solid and if you apply a tangential force, you will get a reaction. Okay, that will be called a shear force or a shear stress. Units are the same, but direction is different. So that's why we will need a tensor to describe a force over an area, because the force that you are going to feel will be different according if it is normal or tangential. In general, you can imagine to take a solid, to take, how to say, a plane. And the plane is described by a normal. Okay? This one, and you have three in general. According to the plane that you're taking to cut your solid and to look for the forces, if it is in equilibrium, these two forces are exactly the same. Otherwise, it's going to shrink. In this direction, they are the same at the equilibrium. But according to the plane that you're taking, you are going to get a different measure of force. That's why we need a tensor. We need an additional component. So actually, the game is over when you think in terms of planes with a normal, and one index will tell you, okay, which direction the normal is, z, x, or y. The second index will tell you the amount of force in that direction. Fine. Now, what about deformation? Well, it's the same game. You can take a deformation along an axis, but as soon as you shrink in this direction, you will get, for normal solids, a shrinking in that one. Okay? You have to describe this. So two indexes. That's why we will need tensors. For fluids, it's not important. Force is described by pressure, and it is a sort of a scalar quantity. Force is a vector, pressure is a scalar, but we will need stress, that is a tensor, a second order tensor. So you can imagine now to take a shear force over an area, same units, Pascal, but you have to take care about the direction that you're considering. That's why solids are a little bit more complicated than fluids. Now, everything will be in any case summarized in a sort of a linear relationship. For example, engineers can look at the same system, but from a different perspective than seismologists. For example, an engineer, let me tell you the end of the story. To generalize that one, for polite solids, that means isotropic solids. This means not crystals, not wood fibers, something that has not a direction-dependent property of a material, instead of k, we will have to use just 2 elastic constants. So it's for lazy people. Instead of 81. That's not for lazy. Why 81? Because we will have stress, a second-order tensor, strain, second-order tensor. And if you want to use a matrix to express the relationship, you will need a 4th-order tensor. That means 81 constants. It's Friday. We will make some, not assumptions, but some consequences of the symmetry principles, and we will be left with 21. Not for Friday. With the final assumption that k will be represented by just 2 elastic constants. They will be called Lamé parameters. And really, for a normal solid, they are enough to describe its elastic properties. Well, engineers prefer to use other 2 elastic constants than seismologists. Okay, I cannot resist. This will be replaced by what we call Lamé parameters. This mu will not be linear density, as in the past slides, but it's called rigidity modules. With these 2, we will find 2 velocities. And you should notice that this shape of the expression is very similar to what we have already studied. For example, Mersen's law in strings, it was the square root of tension over linear density. Some waves, the square root of bulk modulus over density. You see, it's the same. Okay, that's why seismologists prefer to use lambda and mu, because velocities are immediately represented by these 2. Engineers prefer to use something that can be measured in a different way. For example, let's take a sample, let's apply a force, let's measure how much it's going to be elongated. Okay. The proportion between the applied force and the elongation that you get usually is called Poisson modulus, still French, or modulus of elasticity, or Young's modulus, English. The end of a story is always a straight line. Now imagine to apply this experiment here. You will get an extension that you can measure. You will get a shrinkage in the lateral dimension. Okay. The ratio between the elongation and the contraction is called Poisson's ratio, and it's a pure number. Okay, engineers prefer to use Young's modulus or elasticity modulus and Poisson's ratio. Just 2. They are the same. You will see this. Just to say to you that in any case, for Hookean solids, there will be a line there. But we have to generalize that concept of a line.
Sorry, you said that if we put stress in something, it will break after a while. So
No. Look, in the pure Hookean world, this line has no end. In reality, that line, sooner or later, is going to change. It can be broken. What does it mean? Okay, no more reaction. The system is over. Or maybe if you take I don't want to break it, but if you take something that is going to, if I take the lab that we are using, and if I apply enough force, it's going to be deformated permanently. That will be plastic. So it's no more a line. It's something that is going to change. And when you remove the force, the system will not go back to the initial configuration. A broken system, a plastic system, are not these ones. But we're going to stay there. Okay?
So when you go beyond the elastic limit,
No, we don't go.
okay, so Hooke's law doesn't apply anymore.
It's no more a Hookean solid. Jokes apart, in the second term, you're going to have a course also with Karim, and he's going to speak with you about also beyond this limit. In seismology, we will go beyond this limit, but for a different purpose, to understand anelasticity in the Earth. That's different, the Q. So there are many ways to go out from this line here. With me in seismology, we will go out from this line adding an imaginary number. Still it will be linear, but anelastic. With Karim, you will go beyond this limit, speaking about fracture mechanics. But I don't want to break things, okay? So what's next? Okay, this is a worthy stress strain. This is what we're going to do. Now, the first terrible part, deformation. Now, actually, what we're going to do will be nothing else than a generalization of a step number 1 that we did for sound waves. Now, do you remember? Yes, you do remember. What is step one for the building of sound wave equation? We have been considering a volume. We imagine a displacement field there. We imagine maybe a decompression and density was changing. Imagine a compression and density was rising. If you remember, the change, the local change of the properties was related to the derivative of a displacement. du over dx. For a gas and for one dimension perturbation, that was enough. For solids, it's not. Because if you stretch, it's going to change in the other direction. So we will have to take care about the derivatives in all the directions. That will be the strain tensor. That's why what we're going to do now is a generalization of that one, of that step. In these slides here, the representation is in 2D, but it's just because I'm lazy. You have always to imagine a third component, because we have to deal with space now. Okay, but we have an initial segment, and we're going to apply a deformation. So this segment here will become that one after an application of a displacement field. The displacement field is the perturbation. Okay, delta x has become delta y. Now, what we really want to study is the change of property from delta x. So what we can do is to build what has been deformed. So you see that, delta x has been translated here plus the deformation. We do not want to study pure translations. If I'm going to move this table without friction, that's not a dynamic configuration. I want to understand the perturbations of the status of the equilibrium of this system here. So what we do really want is not delta x, is not delta y, but delta u. That's the deformation, like in the gas, delta x. Okay, how can we write it? Well, the trick is the same. To apply Taylor's expansion and being lazy. Just considering gentle perturbation, so that the first term is the important one. Okay. Now, what about delta u? It will be the difference between the displacement applied here and the displacement applied here. Now, as at the time, we write this one in terms of Taylor, and we truncate to the first term. And now wait a second. There is a convention that is abused, maybe, but it's done for a nice purpose, to get over a little bit of indexes. So you see, now we are in space, and the Taylor expansion should be a summation over all the possible derivatives, not just one. At the time of gases, we've just been using just along one direction. Now we have to consider these derivatives in all the directions. So the Taylor applied here minus this one is going to give all these ones. Remember that now we are dealing with vectors in space. Okay? So here we should take a summation over all the possible running indexes. So it should be the ux over the x, the ux over the y, blah, 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 blah. There is a way to, how to say, truncate this, not truncate, to summarize this summation using repeated indexes here. So when you see the same index, it's saying to you, okay, remember, you have to sum over that one. It's called the convention over repeated indexes. It has been created by Einstein a long time ago to deal with relativity. It's just a different way of writing this one into this one. And this summation here is nothing else than the generalization in space of our old du over dx. Because now u is a vector, so it has ux, uy, and uz. And you have to take care about delta ux, delta uy, and delta uz. So instead of writing this one, we can write this one. Ui are the components of a displacement that I am applying here. It has a component in x, y, and z. How it's going to deform it? Okay, we have to take care about the three possible directions.
So I will learn from 1 up to 3, that means?
Which one?
I.
KK.
I. What is the range of I?
It's written here. If you want to live in 26 dimensions, you can do it. But we are living into 3 dimensions.
Okay.
1, 2, 3. So it's 1, 1, 2, 2, 3, 3. Plus, plus, plus.
So altogether we have 9 components.
Good. We are living in 3 dimensions. So you have to take care about x, y, and z. That's it. Why in the gas we have been using just one? Because we consider the perturbation only along x, and the gas was not reacting laterally. Now, let's imagine that your ui is just ux. Okay? So I is x. But now you have to take care about the deformation of x, y, and z. So the ux over dx, delta x. The ux over the y, delta y. The ux over dz. I'm sorry, it's 3 dimensions. No way out. So actually, the 2 indexes of a strain are already here, I and k. Why? Because if you take care about the partial derivatives in all the possible directions, along the possible directions, actually, it's this. You have been right saying 9 components. xyz, xyz. You will see how simpler this one will become in some specific examples. But first, we have to play a trick. Since you are much younger than myself, you should remember the properties of symmetric tensors. Do you? Well, when you have a tensor, it's really nice to have a symmetric one. Why? Well, because instead of 9 components, you can remember just 6. And you can diagonalize a symmetric tensor. So you can find a system in which all the elements are just the diagonal ones, and you're left just with 3. That's perfect for lazy people. Now, this one, in principle, is not symmetric, not necessary. So that we can play a trick. We sum and we subtract the same quantity, like this one minus this one. If you write it out, plus minus, this quantity is exactly this. But this one, if you change y and k, you will see it's a beautiful anti-symmetric tensor. And what is it? Well, it's just describing possible rotations. For example, if I apply a displacement here, what I'm going to do is going to apply a rotation. You do it every day. We hope that they are not going to close the door. But in principle, if you apply this, it's going to rotate. It's not a wave, it's a rotation. So like when we want to neglect translations, we just move this, we can neglect pure rotations because they're not changing anything, nor volume, nor the shape. And we throw it away. What we have left is with this. And now it is symmetric. If you change y and k, it will be purely symmetric. So by definition, the deformation tensor, that properly is for small deformation, so that we can take just the first term in Taylor, like as we did for the gases, in all the dimensions, with this notation here, is becoming the strain tensor. How it is made? Okay, in 2 dimensions, but just for laziness, it's this. Now, you will see in 1 second the picture, and you should be able to understand how this is just a generalization of this. Now you see, it's symmetric. So this one is equal to this one. What is this? Well, this is the relative change in x due to a displacement in x. What is this? It's a relative change in y given the component of displacement in y. Now, in one slide, we're going to find the property. But let's think first. Let's imagine that the 2 derivatives are positive. What's going to happen? If the derivative along x is positive, the displacement here will be larger than here. Let's imagine this is 0. The net effect will be a deformation that is going to enlarge this dimension, right? Like in the case of the gases. And also about y. So if the 2 derivatives are positive, the area is going to change, right? Now, let's add the third, the uz over dz. If also that one is positive, we're going to take a volume and we're going to change it in a positive fashion. If those derivatives are negative, we are going to shrink. So now you're getting the point. The diagonal elements are telling us how much the dimensions are changing. Dilatations and compressions. It's like sound waves, just generalized to 3 components. What about the diagonal terms? Diagonal terms, let me show to you an example immediately. It's in the next page. Let's give a look to it. Let's consider the first panel here, the first cartoon. Look, in 2 dimensions, but you have to imagine the third one, okay? This is coming from your textbook, Steiner West session, okay? Have you been able to find it? In a legal way?
Yes.
Well, if not, don't tell it to me. Now, the first cartoon is about a very simple case. Look, U2 is 0. What does it mean? Okay, no changes along Y. And this one is positive. What's going to happen? If you take the element, you're going to stretch it. If it is negative, you're going to shrink it. That's a very simple deformation. It is exactly the generalization to 2 dimensions of this. And now if you imagine the third direction, it's going to change the volume. If it is negative, you're going to shrink it. Okay? Now, let's imagine this one. This is the real new vision. Let's read here. Now, the 2 derivatives, ux in x and uy in y, they are 0. We have just one element that is different than 0. du x over dy. What does it mean? That the displacement is getting larger along y in the x direction. If you give a look to the cartoon, you will see that now the volume, the area, in this case, has not changed, but the shape, yes. So it's a pure shear. No change in the area, but you have changed the angles. This is the meaning of the diagonal components. Okay? In this cartoon here, now you see that we have both the u1 over dx2 and the u2 over dx1. Again, you are going to change the shape, but not the area. In the last one, you can change whatever. So that matrix, that is symmetric by definition, is telling us what's going to happen to the shape and the volume of the body. The diagonal terms will tell us how much the volume has changed. If they are positive, okay, it's one, you're going to enlarge the volume. If they are negative, you're going to diminish. The diagonal terms are telling us how much the shape has changed. The diagonal terms in fluids, they are always 0. And for fluids, the strain tensor is just becoming a diagonal with all the terms equal. So we are generalizing what we have done for solids, for gases to solids. The bad news is that we have to take care about more indexes. And remembering that we can deform a solid also by shape. While for air and ideal water, we cannot shear it. No changes. We can just compress it. So we generalized that version in order to be able to treat solids. There is a very important property that is related to the symmetry of a strain tensor. Now, please do remember, since you're young, your courses in geometry or linear algebra, something like that, when you deal with matrices. If you have a symmetric matrix, you can always solve the so-called eigenvalue problem. And the matrix is representing a linear transformation. And you can imagine that when you apply what we're going to call the strain matrix to an initial configuration, you're going to have the perturbed one. Eigenvalues problem. When we can write that equation in terms of simple scalars. If you do, and I hope you do remember your linear algebra, how to find these lambdas? Well, you have to take this, solve it. You will get a linear system, now in 3 dimensions with 3 equations, whose unknowns are the lambdas. And you can do it every time that you have a linear symmetric transformation. And this is why. What is the solution? Well, when you find the solution of the lambdas, it means that you're referring to the principal system. In the principal system, if you align along it, the matrix will become just with diagonal terms. It's called diagonalization. And those 3 numbers will tell you how the dimension is changed along the 3 axes. Lambda 1, lambda 2, lambda 3. Every symmetric tensor can give to you, of the second order, is going to give to you 3 numbers. What are they telling to you is that in the principal system, the first is going to tell you how much has changed the x direction, how much has changed the y direction, how much has changed the z direction. There is a final and important property. The sum of the 3 terms, that is called the trace of a matrix, is invariant. In these 5 minutes, I'm using the only, how to say, previous knowledge from your side, linear algebra. I don't remember it. But please do remember that every symmetric tensor, in our case of the second order, can be diagonalized. And if you align along what we called the principal axis, the eigenvectors, if you want, you will find 3 eigenvalues, and their sum, that is called the trace of the matrix, is an invariant. Whatever reference you take, that sum is giving to you the same number. Now, before going to the next slide, let's imagine that I'm telling you that lambda 1 plus lambda 2 plus lambda 3 is positive, the sum. What can you say? Is it Friday? Yes. What can you say?
That's the expanding.
Yes. If I'm going to tell you the sum is negative, right, I'm going to tell you it's 0.
No change. There is no force.
No.
Reshape.
Or they are equal.
Right. It means that you have a perturbation that is giving no change in volume, but maybe it's changing the angles. So now you do realize, as in that strain matrix, you can diagonalize it or not, but the sum of the diagonal terms will always be a number. It could be positive, could be negative, could be 0, and you may have a perturbation, but it's just changing the shape. Of course, if no change in shape, well, we can go, because you take your sample and it's still pure. So diagonal terms are in some way telling us how much the volume is changing. The off-diagonal terms are going to tell us how much the shape is changing. And this is a very important property that we can generalize with a very important slide. Now, some algebra, I'm sorry for that, but elasticity is, okay, we are dealing with continuum mechanics, so it's classical mechanics, no atomic potential, but we have to make some algebra. Now, as I told you, it's symmetric. The trace is defined by the sum of the diagonal terms. It's invariant. So it's this number here. And we understand that it is related to the change in volume. Now let's make a thinking. Can we measure how much is the percentage of change in volume? I hope you do remember something. Oh, I was not writing it. Let's call this sound. No. Let's call it V. I hope you do remember the expression of the velocity. I put the PDF in the new lecture as bulk modulus over density. Okay. Now, let's imagine to have an initial volume V0. So we have our sample. Let's imagine that we apply a deformation to it. Let's compute the new volume. Well, the new volume will be the product of the first dimension, second dimension, third dimension deformed. And by definition, this is the new length, the new length, the new length. Okay. Let's write this product, let's expand it, and let's throw away all the second order terms because it's a small perturbation. What we are left with is with this repeated index summation. And that's the initial one. Let's compute the percentage of change of the volume. So delta V over V, 0. Okay, if you compute it, this minus the initial over the initial is just the trace of a strain tensor. And you can write it like that, repeated index like that, or you can expand it. And what is this? That's the divergence of the displacement vector. You can write it with this, or with this operator, that is the nabla scalar u. These are all different ways of writing the same thing, that is the trace of a strain tensor. Now, I hope you do remember the definition of the bulk modulus. Definition of the bulk modulus was for a gas, for a liquid. Okay, let's take a volume. Let's apply a pressure on all the same pressure over all the faces. Let's measure the percentage of change of volume. That one. Okay? P over that one was the bulk modulus, and it was related to sound waves. Now you can imagine immediately that the divergence of u, the displacement that I apply to a body, is related to its change in volume. It's it. And it's nothing else than the generalization of this. Sound waves. From the divergence of u, P waves will come. So please remember it just since now. That's a property. We did nothing. We just defined the strain tensor, generalizing this, taking care about all the possible directions because we are dealing with solids. We make it symmetric. We computed the trace, but it's an invariant. And we found that the trace is related to the changing volume of what we are doing. Okay? Good. Please remember this. Just different names for the same. The physical thing is this one. In many cases, it's written like theta. But it's nothing else than the sum of the diagonal terms of a strength tensor. But physically are this repeated index. If you unwrap this repeated index, as you were asking before, here you go. So it's how much is changing the perturbation in x, in y, and in z. And you can imagine that if they are all positive, that will be, of course, a positive change of volume. If they are all negative, negative. If zero, no change in volume. Okay, so that's the trace. Now, a small check before generalizing forces. What we did was to say, okay, let's imagine that our perturbation is small, so that we can truncate the Taylor's expansion to the first term. Let's make a check. It's a sort of a prequel. Is it really small when a seismic wave is passing? Well, this is a small check just telling to you that if you take a large earthquake, we will see in the second term how to define magnitude, but it's a sort of a measure of the energy released by an earthquake in terms of seismic waves. So if you take a big one, and if you stay at a given distance from it, the wave that is passing, that is making some buildings to shake and to collapse, unfortunately in some cases, but if you measure the deformation that is carried by those waves, actually, it's really small. Like this, for sound waves, these are gentle perturbations around the equilibrium of pressure at the beginning. Okay? It's small. So we can go on. Sorry, but we have to go on. What to do next? We have generalized this. And x, remember at the beginning of the course, it was the displacement from the equilibrium. Then we consider the displacement from the equilibrium as the derivative of an external field of displacement to the equilibrium of the system. And now generalize this in 9 components that are telling us how much displacement is making the system to change. Symmetric, the trace. Now we have to deal with the F. And the first part is easy, because since this morning, the beginning of this lecture, you had been asking for force over an area. Good. So now we take an elastic solid here with a given volume, and if it is at the equilibrium, at the beginning for example, or if we imagine to apply a force system to it, we can imagine to apply it to a unitary surface. Now, what is the problem here? That a solid has an initial shape. A gas has not. A fluid has not. It's trying to go back to make a free surface, but has not a definite shape. A solid, yes. Okay? And so, every surface in it has to be specified. For example, this one has a normal that is pointing along Z. Now, let's imagine that I'm applying a force in this direction. Well, this force is a vector, and I can imagine to decompose it in a horizontal one, tangential, that will have an x component and a y component and a z one. In summary, the normal of a surface is not always parallel to the force. So we have to decompose it. Let's begin. At the beginning of the definition of stress tensor is here. You have to imagine a traction. It's a vector. So it has one index. It's applied to an area. And now we have to imagine that the traction applied here to an area that has a normal n is this. Look, vector as a function of a vector. That's the origin of the two indexes that will cause the force to be generalized to a second order tensor. Nothing more, nothing less. So T applied to a surface that has a normal. For gases and liquids, we don't need it. A gas has no shape. So it's always normal if you want. Okay, let's give a look to the units. In principle, they are Pascal. Force over an area. Newton over square meters. Pascal. Do you agree with me? So the units are fine. Directions, we have to work on that because we have now two vectors. The normal and the direction of the force. We have to decompose the second one and also the first one with respect to an axis, to a system of reference. That's the problem. Of course, when everything is in equilibrium, and remember, in statics, the equilibrium is given by two conditions. All the resultant forces, the sum, has to be 0. All the momenta, the sum of each single momentum, the total momentum has to be 0. Otherwise, I can open the door, and we hope that we can open the door at the end of the lecture. That's why, in the equilibrium, the traction applied along n has to be equal to minus the traction on the opposite side. That's in the equilibrium. If you want, it's the third law of dynamics. And if the total force is 0, okay, it's one of the conditions of equilibrium.
So it's an example of an odd function.
Of n,
Odd function.
why?
Because when you take t of negative n, it gives you negative t of n.
In that sense, I would say yes, but it's more than a function. I mean, it's a function, is a vector function and a function of a vector. So if you want, it's a node. How did it make it? Let's say yes, but let me say also no. Now what to do? Again, once you understand that is nothing else than the choice of an area, of a plane, that has a normal, the game is over. For example, let's take a beautiful cube that, respect to our reference system, has faces parallel to this axis. Okay? Now let's consider the tractions that are acting over it. Look. And let's consider, for example, this one. Now, T is a vector. It's going here. And it is referred now to a face whose normal as a vector, a face whose normal is a vector. And here it is written 2. Why? Because the normal is 2. Okay? How to describe this vector that is a function of a vector? Well, let's decompose it. It's a vector. It will have 3 components. Right? So you see here, it's T of 2 vector, but now is going to describe the 2 component, the 3 component, and the 1 component. Game over. That's the origin of the 2 indexes. Once you take down this index here, T22 means the force that is acting on a face whose normal is 2 in the 2 direction. Game over. Of course, this will be normal, this 2 will be tangential. So it's nothing else than a decomposition of a vector respect to a face. For gases, it was not necessary. They have not preferred faces. But this one has. So if you take a system like that, that's X, that's Y, that's Z, well, you can change it. And now if you have a force here, you have to decompose it according to a normal. In an algebra sense, remember that here we have a vector as a function of a vector. Then you decompose it. Then you write it in terms of scalars, and what you're left, according to your reference system, is this. Well, that sigma I of j is the stress tensor. What are the two indexes? The first is telling to you the direction of a normal of the face. The second is telling to you which component respect to that face. Game over. Now, before proceeding, and it's written there, let's imagine to do it for a gas. Well, we take this plane here that has this normal, and we measure. Oh, that's pressure. Let's take another one, and let's measure. It's the same. It's always the same. Actually, that sigma, in the case of fluids, of gases, and ideal liquids, is just becoming pressure. All the diagonal terms of diagonal terms will be 0, and on the diagonal it will be just P. That's why it's a generalization of force and pressure. Now what we have to do, also if it is Friday, is to consider this one for a face that is not oriented according to one of the principal the reference axes, like this one. What is the game to be played? Well, it's easy. You see this face here as a normal that has 3 components. So you decompose n in x, y, and z, and then you decompose t respect to x, y, and z. So to sum up, there you go. The first index of a stress tensor is telling to you the direction of the normal. The second index is telling to you the direction of the force acting on that surface. Now, how many components? By definition, a stress tensor has 9 components. What about Friday?
6.
How to make it to have just 6? For the strain, we did it. We created a symmetric tensor, removing the anti-symmetric component. What can we do?
Diagonally?
But wait, who is telling you that it is symmetric? I'm going to tell you that it is symmetric, otherwise we will not stay here. But if you want to demonstrate that it is symmetric, there is some algebra to be developed. No, it's a couple of pages of algebra. But let me tell you that it's based on conservation principles, conservation of momentum, especially. But one can show that stress tensor is symmetrical. Okay, and now we are happy. So, not by definition, but by demonstration, stress tensor is symmetric. So that we have just 6 components. And we can diagonalize it. And we can find a reference system for which all the elements are just diagonal, and the sum is the trace is invariant. And now we are happy. We are so happy that the end of the story can be summarized here. So you take your sample. You can write all the 9 components of a stress tensor. Now you see them. What does it mean to 2? The force that is acting along 2 on a phase whose normal is oriented on 2. Okay? And there you go. And if you want to go back to the ideal fluids case, that tensor is going to shrink into a number. Just diagonal, and all the diagonal terms are P, P, and P. And the units are those of pressure. Now, before moving on, and to conclude this part, what are the units of a strain tensor?
No, inches.
Right, because it's a length over a length. Actually, it's measuring the percentage of variation of lengths in the different directions. So please do remember that in the case of Hooke's law, one was force, the other was displacement, and K was a force over a displacement. Now we generalize stress in terms of a pressure and X in terms of a matrix of pure numbers. So that, I'm telling you just now, when we are going to put together stress and strain, and they will be related by elastic constants, these constants will have a units of stress, so that pressure. Okay? Good. Okay, that would be perfect for lazy people. In the sense that, now, if we don't want to study this, but just to study statics, you see this table is not floating. I hope. The door is not opening. We hope it's going to be open. But what does it mean? That for statics, what we have to write is to write that all the forces now are balanced. Internal forces, okay, it's not going to explode, and external forces. What about gravity here? What if I release this? It's not in equilibrium, it's going to fall. It's going to break beyond the elastic behavior, but okay. And then on the pavement, it will stay there. Why? Because the pavement is going to offer a reaction. So it's in equilibrium. This as an object, as an internal equilibrium, it's not going to implode, I hope not to explode. And now it has also an equilibrium compared to the external forces. What does it mean? That for the equilibrium condition, and we want not to study this one, we want to study dynamics, but for this slide here, equilibrium, what does it mean? All the forces have to be zero, all the momentum, all the momenta have to be zero. Well, the first one is going to be relaxed in the next slide, when we're going to deal with dynamics. And you know, if the force is not zero, it will be equal to mass and acceleration, Newton. The second one can be used to demonstrate the symmetry of a stress tensor. But before looking at the yellow box, I'm going to ask you, why I'm using here two kind of forces? Because you see, the first term, and this is going to be tricky, The first term is an integral over volume of all the what we call body forces. Do you want one? Gravity. That we are using now, okay? It's called a body force. Gravity is acting on the total mass of the body as an external force. Do you want another example? Well, a magnetic force, if you take a magnet and a piece of iron, but a body force. The other ones are the integrals over all the possible surfaces here of internal elastic forces. Okay? So you have to learn now the difference between body forces that are acting on the bulk mass of something like gravity and internal surface forces that are the forces that are keeping this table together as a piece. No elastic forces? Well, it's going to be a set of free particles. Okay. And now we're going to discuss the yellow box, but then I want you to think again about this. Now you take the first expression. You can write the second element and replace it from an integral over surfaces using Gauss' law as an integral of the volume. And if you go back to the expression of T of I, that is here, this one, this term here, it becomes an integral over V of this. Now, have you ever seen an expression like this?
Yes. Continue.
Continuity equation actually was this one, and we generalized that. But we are not that far. Because if you do remember, we made 3 steps to build sound wave equation. The first one, we said, okay, let's apply displacement, let's see how density is changing. If density is changing, pressure, local pressure is changing. If pressure is changing, we have active forces and we have acceleration. Actually, the second element where the cursor is pointing is the generalization of step number 3. Do you remember it? We said we had been writing something like that. And we said, well, wait a second. If this is a force, this has to be Newton. Actually, if we want to move from statics to dynamics, we have to do exactly that. And this is what we're going to do. I'm going to tell you. This is what we're going to do. And we're going to find wave equations. But if you do remember, that was the third step. And now if you give a look there, we generalize delta P, stress, and now we have to move just in all the possible directions. It's just that. But, bad news. Because we have to deal also with this. Now, do you remember one of the first unofficial homework? It was the spring connected to the ceiling with the mass. And that asked you how to deal with this system. And the answer was that, okay, if we are smart enough that we take the new equilibrium position and we start from that one, the equation is exactly the same as the horizontal one. if we are smart enough, but we don't consider this table under also the effect of gravity, but we want to study the perturbations around this equilibrium here, we can neglect gravity. Because what we want to understand are the vibrations due to this. And that will be the trick that we're going to play. We will consider the Earth as in a pre-stressed body in equilibrium. And we will start from that part, and F will be thrown away. Okay, let's make a summary of what we did until now. We said we have a solid that is behaving linearly under small perturbations. How to describe perturbation? Strain tensor, symmetric. How to describe the possible forces? Stress tensor, symmetric. And the stress is given dynamics. If no resultant force, if no resultant momentum, it's in equilibrium. And of course, we're going to study this. And this is what we're going to do. But now we have to deal with body forces. Okay, it's in equilibrium. Gravity, reaction of the pavement, over. We start from here. So if I put my telephone here, I've already shown to you the vibrations of the table, not of the sound. Yes, I did it. Okay. So when we study both vibrations, we can neglect gravity if we start from this equilibrium condition. Okay, just a sum up of statics. These are all the possible forces acting, for example, on a square. You see, body forces are applied to the center of mass. What about the other forces? Well, in this reference system here, we have sigma 2 and this and this. All the sum of these ones, along all the possible directions, has to be zero. Statics. If not, dynamics. And so accelerations. Okay, and this is another vision in 3D instead of 2D. So please remember that due to the symmetry of the tensors that we defined, stress units are Pascal or better bars. Especially for the Earth, it will be more important to use bar. It is not that far from 1 atmosphere. Remember, due to their symmetry, we can always find a reference system for which all the stresses are just diagonal. And we take 3 numbers, and the maximum is called the maximum compressive stress. The reference system is called, okay, the principal stress axis. The same for strain. It's due to the symmetry of these tensors. Let's make the final step for today. Let's generalize it. Now, if we want to couple stress and strain, we need this terrible 4th order tensor, 81 components. No. Because due to the symmetry of the strain and stress tensor, some of these elements and conservation of energy, from 81 we can go to 21. No. Now, if we apply the condition that the solid that we are dealing with is not made by fibers that are elongated along specific direction. It's not a pure crystal, but it's a normal solid. It's called isotropic. And then what is left is just this. Now, this is what we have to put in our pocket today. Stress, strain, the relation. How it is made. And this is called generalized Hooke's law. Let's give a look to it. We have 2 elastic constants. They are called Lamé parameters, lambda and mu. And in the last 10 minutes, we're going to give a look to their meaning. First, please do remember that their units are Pascal or bars. They are the same units of stress. Good. Let's give a look to the first, lambda. Well, if you notice there, and you will see in the next slide how simpler this appears, this is just acting on theta. Theta is the quantity that we studied a few slides back. Yes, it's related to the percentage of volume change, percentage of change in volume. The divergence of you, the sum of a strain tensor, all the different writings. So lambda is acting only on that. Lambda, actually, will be very similar to B. Plus another constant that now is acting on all the possible directions. Wait a second. Because when you write it, when you expand it, it appears like that. That's stress tensor written in terms of the strains. Please do remember one thing. What are strains? Strains are nothing else than different derivatives of a displacement vector. And actually, this is what we're going to use when we will put everything together, like when we solve this equation, saying, wait a second, delta P can be written in terms of variations in density. Variation in density can be written in terms of this, and we found an equation. We're going to do the same. But if you fully write it, there it goes. Now, what do you notice is that on the diagonal, lambda is acting here. On the off diagonal, it is not. Some terminology. Please remember that this matrix here, that is nothing else than the stress tensor written in terms of strains, is diagonal. So we can compute the sum of the diagonal terms. It's an invariant, and that will be called mean stress. And it's like that. And it is nothing else than the sum of the eigenvalues, by definition. Now, that mean stress will be the equilibrium condition from which we will move. And with that trick, gravity will go out. Okay. So actually, what we are going to study will be this one. And if you want to stay in a very gentle Earth system, what is the stress caused by the mass of a material going inside the Earth? It's just the weight of what's up. 0, well, there is the atmosphere that is negligible, and then you can go, you enter inside. That will be the initial mean stress, the weight given by the mass over our heads. Lithostatic. That will be the initial configuration. But I want to conclude with something that will be nice, I hope. But wait a second. What are the meaning? What is the meaning of lambda mu? Okay. And this is mainly the final slide for today, but it is the most important one. So we are going to give a look to it. Then we will make a 1-minute pause, and then if you want, you can ask questions. Let's give a look to what is mu. Well, mu, if you go back by one slide, is the ratio between shear stress and shear strain. It has the units of course, stress. And what does it mean? Okay. If we take a solid, and if we apply a shear stress, we can measure the shear strain. The ratio is mu. What about a fluid? Well, in a fluid, we can apply the stress and we have no strain. So it has no meaning. Mu is going to be called rigidity modulus. And what does it mean? That if a solid is very strong in terms of rigidity, lateral rigidity, I can apply any stress here, but I'm going to get no strain. So actually, mu, as a paradox, will be infinite for infinitely rigid shear solids. And it's going to be 0 for fluids. Okay? It's called rigidity modulus. And its meaning is easy. I take something, I apply shear stress, I measure the strain. So it's like Hooke's law, but for shear. Rigidity modulus. From infinite, you cannot move it, to 0, no reaction, fluids. And that's easy. What about lambda? Well, lambda, we have seen, it's connected with the diagonal terms. It is related to change in volume. Now, let's compute bulk modulus. Now we go back to our old definition of bulk modulus. We take a sample with a given volume at the beginning, and now we apply pressure over its sides. Now, it's different than gas and water, because if we apply something in one direction, it's going to move also in the other one. So it's a little bit different. It's also dependent about mu. Actually, if you take the ratio between the pressure that you apply and the relative change in volume, that's bulk modulus, what you get is this. Now, if you take a fluid, mu is 0 and b is lambda. So you do understand that if you take a solid that is not a solid but has a 0 mu, we go back to the old theory. We have no mu's and lambda is b. But for a solid we have a mu, and the bulk modulus is containing also mu. Okay? That's why we generalized, if you want fluids. The price to pay is that we have to take care about mu. Okay, now, to conclude the concept that I was telling to you before, let's imagine to be engineers. Let's imagine, or someone studying rock mechanics. Let's take a sample. Let's apply a stress along a specific direction. And let's measure the change in length. Okay. For example, you apply a stress 1, 1. What does it mean? Stress is acting along x with a phase whose normally is along x. Easy. Let's measure how much it's going to be stretched. Let's take a ratio. It's called Young's modulus. It's the parameter that is nearer to this one. What about the units? Okay, the units of stress. You can write this quantity here in terms of lambda and mu. You can do the algebra, and there you go. Now, if you do that experiment, you have to imagine that you have got an elongation or a compression along x, but also a change, a lateral change. That is called E22. If you take this ratio, you're going to call it Poisson ratio. Usually, if you stretch, it's going to get thinner in this direction. That's why you have a minus here. Okay, you can write this ratio in terms of lambda and mu, and there you go. So my message here is, for an isotropic solid, you can decide to use lambda and mu, lambda parameters, or if you want, E and N. It's up to you. For example, if you choose E and N, you can rewrite using these two expressions, lambda and mu, in terms of E and N. Just to elastic constants. For seismologists, it's much easier to use these ones. Why? Because you will see on Monday that the two velocities can be written immediately. And you get immediately now the vision that if you go back to the fluid, this is 0 and this is not existing, and this is a sound wave. Okay? Final word. But we'll deal also with your next homework. But it's too early. If you take Poisson's ratio, for example, as you can see there, what are the limits? Well, let's imagine to take a fluid. For a fluid, mu is 0. And Poisson's ratio is 1/2. The other extreme case, it is a little bit strange, but there are some strange materials, is that you stretch and you got no change in the other direction. And so, this will be 0. Final word. For many cases, important for lazy people, you can take an approximation. But lambda, from a numerical point of view, not from a physical point of view, is equal to mu. If lambda is equal to mu, this will be 1/4. And what is funny is that if lambda is equal to mu, you will see that Vp will be the square root of 3 of Vs. It's a beautiful working hypothesis. Salute. That's Italian for. It's a beautiful working hypothesis because it's going to simplify the life. And it's also a good approximation for many materials in the Earth. When lambda is equal to mu, it's called a Poisson solid. So it's a Hookean solid, and inside the Hookean solids, you can call, with a French name, some solids for which lambda is equal to mu. Now let's end for today with this final slide here, that actually is saying that we generalized Hooke's law starting from a spring and a mass system to something that has springs in 3 dimensions, and these springs are representing now solids, because the interatomic forces are strong, and they have a volume and a shape. And to describe the change of shape, we need mu. And we need the diagonal terms of strain. If we don't care, mu is going to 0. The diagonal terms will disappear, and we are left with pressure in terms of stress, like at the good old times of the sound waves. But now we have an equation that is a little bit more complicated, taking care about the change in volume. And if you change the volume, it will change also in shape. These are the bad news. The good news is that we are going to find a new wave that is called S wave. These are all generalizations of what we did. Remember, we used the bulk modulus, and we found sound wave velocity. Now we generalized it, and it's containing lambda and mu. Then we considered also these ones, very simple, but sometimes they're going to stretch. So Young's modulus and Poisson ratio. And the news is that we can take a solid and we can deform it not with its volume but with its shape, because a solid has an initial condition with a given shape. Okay, that's it. These are some examples of values. You will see how the seismic waves velocity will change. Usually they are very fast. So if sound is 342 meters per second, seismic waves that have much larger B, for example, can be very fast, like 10 kilometers per second. And you see that in some cases here, like limestone or dunite, the Poisson condition is good. And we're going to use it to simplify the algebra. Okay, no, that's not for today. That's not for, let's stop here. Again, today I've used and maybe abused your previous knowledge about linear algebra. We have just played with matrices, 3 times 3, so with 9 elements. But we have used the definition and a consequence, making them symmetric. Every time that you have a symmetric matrix, you can diagonalize it. And the sum of the diagonal terms is a number whose value will be constant, whatever system you consider. If you take the principal axis configuration, okay, just the diagonal terms. But the sum is the same. And in the case of a strain, that sum is telling you how much volume is changing. Positive, negative, 0. And we call that theta. It's the divergence of. In the next lecture, I'm going to abuse your previous knowledge about some vectorial algebra, because we have to play with vector operators, like the nabla one. So the gradient, the divergence, the curl, and we are going to use their properties to simplify things and to find two-way equations. All this material now is going to be covered and overcovered by the textbook. Most of the slides are coming from that textbook, if you need that. Definitely, I'm going to ask you at the exam just the things that we discussed together. Okay? And you will see that the exercise that I will give to you at the exam are very easy. And we're going to spend a couple of hours playing with them, additionally to the course, okay? So relax. That's why I put 2 additional hours, but just as a recap and to do some exercises, okay? And some exercises will be done during your next 2 homework, coming from the Steinway session textbook, okay? Okay, let's go towards myself, a Laura commission, you to complete your homework and to think about the seismic waves that we are going to find on Monday.